Welcome once again in the class of topology, and as promised in the previous video, in this video we will prove that every closed and bounded interval on a real line is compact. So first I am going to write the statement. Statement of the theorem is prove that every closed and bounded interval on a real line is compact. So the proof is based on nested closed interval theorem, which we have proved in the previous video. Let AB, let me denote it by I. Let I is equal to closed interval AB be a closed and bounded interval on real line. For my convenience, I'm just renaming it. Instead of writing AB, I'm writing A1 and B1, and this I'm writing I1. So what I want to show that this I1, that means A1, B1, is a closed and bounded interval, and now I'll show that this interval I1 is compact. Suppose, if possible, it is not compact. We are going on to the way of contradiction. Suppose, if possible, I1 is not compact. If a set is compact, then every open cover of it has some finite subcover. And if some set is not compact, then there will be definitely an open cover having no finite subcover. Since we have assumed that I1 is not compact, so there must be an open cover which has no finite subcover. So therefore there exists an open cover of I, say C, having members G alpha, alpha belonging to lambda, having no finite subcover, That means members of C, their union will cover I, but any finite subcollection of C cannot cover I. Or you can say I is I1, or you can say that I1 is not covered by finite number of members of C. So in simple words, I can write that means I1 is not covered by finite number of members of C. I1 is not covered by finite number of members of C. Now look at, we are talking about the real line. On real line, so this is the real line. Here you are having your I1, A1 and B1. Take their middle point, this one, that means A1 plus B1 divided by 2. This point will break this closed interval into two parts. One part is from A1 to A1 plus B1 by 2, and the second part is from A1 plus B1 by 2 to B1. Or you can say that this I1 I1 means A1 B1 can be written as A1 to A1 plus B1 by 2 closed interval union closed interval A1 plus B1 by 2 to B1. This interval I1, I have broken it into two closed intervals, this union this. Since I1 is not covered by finite number of members of C, so at least one of these two, either this one or this one, at least one of these two will not be covered by finite number of members of C. Because if both are covered by finite number of members of C, obviously their union will be covered by finite number of members of C, which is not true. So at least one of these is not covered by finite number of members of C. It may be the first one, it may be the second one, whatever it is. Maybe the first interval, maybe the second interval, name it as I2. So let I2 is equal to A2 B2 be that one which is not covered by finite number of members of C. So not to confuse, this A2 B2 is not a new interval. Either A2 B2 is this first interval or A2 B2 is this one interval. If it is not covered by finite number of members of C, we will rename it as A2 B2. If it is not covered by finite number of members of C, we will rename it as A2 B2. So A2 B2 is either this one or this one. So suppose your A2 B2 is the second interval, this one. Suppose this is your A2 B2. Once again, take the middle point A2 plus B2 by 2 and break this interval I2 as A2 plus B2 by 2 union A2 plus B2 by 2 to B2. So what I have done, I have broken this interval into two parts, this interval and this interval. Since A2 B2 is not covered by finite number of members of C, at least one of these two is not covered by finite number of members of C. Because of the same reason, if both are covered by the finite number of members of C, their union will also be covered by the finite number of members of C, which is not true because our I2 is not covered by the finite number of members of C. So whatsoever, maybe this interval, rename that one as A3 B3. So let I3 is equal to A3 B3 be that one which is not covered by finite number of members of C. Once again, A3 B3 is not a new interval. It is either this one or this one. If it is not covered by the finite number of members of C, we will rename it as A3 B3. If this one is not covered by finite number of members of C, we will rename this interval as A3 B3. So suppose your A3 B3 is this interval. This is your A3 B3, new interval. Your first interval was this one. Your second interval was this one. This is third, and so on. Once again, this will be reduced by breaking it into two halves, and so on. In this process, we have obtained a sequence of intervals, In. So we have obtained a sequence of intervals, In, which satisfies some properties. What the properties are? Number one, In is a closed interval, in fact closed and bounded for every n belonging to n. Secondly, your in contains in plus 1 for every n belonging to n. Your I1 contains I2, your I2 contains I3, I3 contains I4 and so on. That means it is a nested type of closed intervals. This sequence is a nested sequence. Thirdly, length of in approaches to 0 as n approaches to infinity, because these intervals are going to be shortened in each step. This, then this, then this, then this, then this, then this. So this length of in is going to tend towards 0 as n approaches towards infinity. So this is a nested type of sequence of closed intervals. And in the previous video you have proved nested closed interval theorem, that if there is a nested closed intervals sequence, then its intersection is not phi. So therefore by nested closed interval theorem, intersection of these all i's n belonging to n is not phi. One more thing I want to mention here. This is 1, this is 2, this is 3, and there is one more point, 4. There is one more point, 4. And what this 4 is? This is each of these ins are not covered by finite number of members of C. Your I1 is not covered by finite number of members of C. Your I2 is not covered by finite number of members of C. Your I3 is not covered by finite number of members of 3, and so on. Every in, it is not covered by finite number of members of C. It may be I1000, it may be I10000, it may be any in. So in is not covered by finite number of members of C. Now intersection of in is not phi. Since intersection of in is not phi, there must be some element. So let x belongs to intersection in, where n belongs to n. Now this x belongs to intersection. That means x belongs to each of the ins. This means x belongs to in for every n belonging to n. In particular, you can say that your x belongs to I1. In particular, you can say that x belongs to I1. But I1 has an open cover, C. So I1 is a subset of union of members of C. So that means x belongs to I1 and I1 is covered by this. So x belongs to this union. And x belongs to this union means x belongs to some G alpha. So therefore there exists some alpha naught belonging to lambda such that x belongs to G alpha naught. Now x belongs to G alpha naught, and G alpha naught is an open set. And when x belongs to an open set, then there will be a neighborhood of x such that x belongs to that neighborhood, and that neighborhood is a subset of open set. So definitely, therefore, there exists epsilon greater than 0 such that your x belongs to the neighborhood x minus epsilon, x plus epsilon, and this x minus x plus epsilon is a subset of G alpha naught. So I am removing this from here. Now your this interval x minus epsilon, x plus epsilon is a subset of G alpha naught. Also, length of In as n approaches infinity is 0. That means your interval In, it is continuously shrinking. It is going smaller and smaller at every step. And since the interval is shrinking continuously and every In is containing x, and this is the neighborhood of x, so there is x, this is your x, this x belongs to I1, I2, I3, I4, I5, I6, I7, I8 and so on. This x belongs to every In. X belongs to every In, and you are having a neighborhood x minus epsilon, x plus epsilon of x. And this In is continuously shrinking. So at some step, maybe after a large number of steps, there will be some interval In which will be contained in this x minus epsilon, x plus epsilon. So there exists, since limit of In as n approaches infinity is equal to 0, therefore there exists m belonging to n. Maybe m very large, maybe m 1 lakh, 2 lakh, 10 lakh, 1 crore, maybe any large number, but definitely there will be m belonging to n such that the interval at the mth stage will be a subset of this. Now Im is a subset of this and this is a subset of G alpha naught, means Im is subset of G alpha naught, and G alpha naught is a member of C. We were saying that each of these I's is not covered by finite number of members of C, and what we are looking here, that this Im is covered by just a single member of the set C. I think you have understood the point. This Im is covered by a single member of the set C, but in the fourth point I have written that no In is covered by finite number of members of C, and this is a contradiction. This is a contradiction, and why this contradiction is there? Because our supposition was wrong. In the starting we have supposed that if possible let this interval I1 be not compact, and that was wrong. So this means I1 is compact, and that what we wanted to show, that every closed and bounded interval on real line is compact. So we have proved this theorem. In the next video we will prove more and more theorems on compactness. Till then, thank you once again.